You should by now be very familiar with the idea that a graphical profile like this can be used to represent the amplitude transmittance of a sinusoidal, or more strictly a cosinusoidal diffraction grating with a period d. But you also know that we can equally well represent the same information by showing what spatial frequency components make up the profile. In this particular case, there's a component at q equals 1 over d, another at minus 1 over d, and in order to keep the transmittance always positive, there's got to be a zero frequency component as well. Now, the beauty of this model is that it then provides an explanation of why, when a laser beam of light, say, is diffracted by a sinusoidal grating, the diffraction pattern consists of just 3 spots. But you also know that you can add sinusoidal transmittances together to create more complicated gratings, such as this square wave grating, for example. Here, the profile is made up from a large number of sinusoidal patterns, each with a different frequency. And this is very obvious when you look at the alternative representation. You can now see that we've got a series of frequency components with both positive and negative amplitudes, and once again a zero frequency component to keep the whole transmittance positive. Now, the aim of this program is to expand this repertoire of spatial profile, spatial frequency pairings, so as to encompass a much wider range of possible diffraction objects.
Well, the trouble so far is that we've only been considering gratings that we could consider to be infinite. And the trouble with that is that in the real world, infinite gratings simply don't exist. And the reason that we've been able to get away with it up to now is that across the width of the laser beam, there have been very many grating periods. To all intents and purposes, the grating has been acting as if it were infinite. For example, consider this one. This is the diffraction pattern of a square wave grating, which can be considered to be infinite. Well, let's get into that and have a closer look to see how it might change as we consider different cases. There we are. We'll just concentrate on those 3 spots there. Consider this. Quite a lot of structure between the spots now. And what about this one? Quite different. You see, what we're doing is making the grating, in a manner of speaking, less and less infinite. And we've ended up with the limiting case of just having a single slit. And the intermediate case that we pass through, what do you think that is? Well, it's simply the case of a restricted grating. How is it that we can account for the diffraction patterns of gratings that, not even approximately, can we consider to be infinite?
Well, that's not a very easy question to answer, because, as you know from the units, when we go to a non-infinite object, we need a whole range of spatial frequencies to synthesize its transmittance profile. And working out all the appropriate relative amplitudes of these frequencies, by hand, so to speak, is no trivial matter. So what I've done here is program our computer to work them out for me in a number of different cases. And to start, the transmittance profile of the square wave grating, varying in space as a function of x. I'll now get the computer to calculate its spatial frequency components. And lo and behold, it gives us the answer we already knew, which is just as well. OK, now let's see how the spectrum changes as I alter the profile in x space. I'm going to leave the width of the pulses alone, but increase the spacing between them. Let's see what the computer calculates now. And let me open up the pulses a bit further. What's happening is that the frequency components in q space get closer together as the pulses in x space get further apart. But do you notice we appear to have the same envelope controlling the amplitudes of the spatial frequency components in all the cases? Let me expand the pulses a bit further still. Well, we've only got 3 pulses in view in x space now, and the frequency components are very close together in q space. But again, that same constant envelope note. I've now gone to just a single pulse in x space, and the frequency components are now so close together that it's rather meaningless to talk about the amplitude of individual components. Instead, we talk purely in terms of the spatial frequency spectrum, so as to deliberately draw attention to the shape of the envelope. In fact, we don't normally plot the frequency components at all, just the envelope. This particular shape is called a sinc function. We say that the sinc function is the Fourier transform or Fourier mate of the single square pulse. Or equivalently, we say that these two representations constitute a Fourier pair.
Well, this is the single-slit diffraction pattern that we met earlier. It's one of our problem patterns, one of the ones that we have to account for. Well, now Keith has developed a theory for it, so let's see how the theory measures up to the pattern. There we are. At the top, we can consider that single pulse to represent the transmittance of our single slit. And beneath it, we have the sinc function, which we can think of as the diffraction pattern produced on a distant screen by the single slit. And I think you can see that there's a qualitative agreement between the actual pattern we obtained at the bottom and the sinc function there in the middle. But of course, there's one qualification we have to make here, and it's this, that the sinc function represents the field on a distant screen, whereas the diffraction pattern is the intensity. Well, of course, all we have to do is to square the sinc function, and I think you can do that in your minds well enough, and you can still see that the essential correspondent remains between the intensity pattern that we actually observed and the pattern that we've derived by theory.
So let's add that result to our summary board. In X space, we've got this square pulse function, which for fairly obvious reasons we call a top hat function. And this has the Fourier transform, looking like this, called a sinc function. OK, so we've now been able to add another pair of Fourier mates to our list. That's the pair that corresponds to a single slit-like object. But be careful, this is just one particular kind of slit. It's got a particular width, and it's got this particular top hat-shaped transmittance profile. The obvious questions to ask now is, how would the frequency spectrum differ if, say, the slit were made narrower? Or if the transmittance profile were a different shape? For example, suppose the object were made on a photographic negative, and you've exposed it so that it gradually changes from total blackness through varying levels of grayness up to total clarity. OK, let's take these ideas one at a time. Let's consider first how narrowing down the width of the pulses changes the spectrum. Back to the computer. Right, so here's my starting point again, the single slit in X space and the sinc function in Q space. I'll now narrow down this pulse at the top. So what's happening here? Well, first of all, the frequency spectrum curve has widened out. Now, that reciprocity is what you might have expected. Narrowing the pulse in X space has widened the spectrum in Q space. But something else has happened as well. The height of the frequency components has also been reduced. Why? Well, think of the physics. Suppose the top hat function really does represent a single slit through which light's passing. Well, the narrower the slit, then the less light gets through, and therefore the less energy. And if you think of that energy as being distributed throughout the whole of the frequency spectrum, then there's going to be less amplitude in the spatial frequency components. They must also go down. As I make the slit narrower and narrower, then the spectrum is going to get smaller and smaller. And this is really rather inconvenient for display purposes, because the relative amplitudes stay the same anyway. So, just for convenience, I've normalized the frequency spectrum. I've programmed the computer to always plot the maximum amplitude at the same height. So let's look at the normalized version. And I'll always do this from now on. Let's narrow the pulse down a bit further. And here the frequency spectrum has moved even further out. It crosses the axis only just before it goes off the screen. An even narrower pulse. And now the frequency spectrum doesn't cross the axis at all. And here in the limit, where I've only got a spike in X space, I've got a continuum in Q space. Well, that's the first problem about narrowing down the slit. But what about the other problem of different shaped slits? Well, as you can imagine, I'm going to ask the computer to give me the answer to that. And what I'm going to do is start with that spike and expand it up into different shapes. And the particular shape I programmed in to begin with is this bell-shaped Gaussian. And its frequency spectrum? Well, you'd be hard put to say this was any different from a continuum. Let's expand up a bit more. Frequency spectrum. Well, it's clearly not a continuum because the amplitude is falling away as we go away from the origin. Let's go on. And the frequency spectrum again. We again have this reciprocity that as it opens up in X space, it narrows down in Q space. In fact, this function is a Gaussian again. A Fourier transform of a Gaussian is a Gaussian. And in the limit, when I have a constant in X space, what I get is a spike in Q space. OK, let me expand this up now with a different shape. I'm starting with a spike and the continuum, but I'll now expand up as a triangle in X space. And the frequency spectrum? Well, this could be a Gaussian. Let's expand the triangle up a bit more. Well, it's not a Gaussian, it's wiggling about. In fact, this function is the sinc squared function. The Fourier transform of the triangle is sinc squared. And in the limit, when I have a constant in X space, I get a spike in frequency space. One final profile. Let's start again with the spike, and we get the continuum in Q space. And I'm going to have two exponential decays in X space. And the spectrum for this well, again, this looks a bit like the bell-shaped Gaussian, but in actual fact, it's called a Lorentzian. Let's go for an intermediate case in this double exponential. And see what that gives us for the frequency spectrum. We expect the frequency spectrum to be wider, and sure enough, it is. And of course, in the limit, I expect the constant to transform once again to the spike. Right, well, let me just summarize those results. First of all, we've got the triangular shaped function, which Fourier transforms to this sinc squared function. And then we had the Gaussian function, which is a special case, remember, because that Fourier transforms to yet another Gaussian. And we also had this double-sided exponential function, which transforms to another bell-shaped sort of function, but it's actually different from the Gaussian. It's different in the wings. We call it a Lorentzian function. Now, there are a couple of things which are important to remember about these Fourier transforms. First of all, the reciprocity between the widths. When the function is wide in X space, it will be narrow in Q space, and vice versa. And the other point to remember is that although we actually derive these Fourier transforms starting with functions in X space, this triangular function, for example, in X space, and working towards the sinc squared function in Q space, it's perfectly possible for me to have started with, say, the sinc squared function in X space, and then I would have worked out that the Fourier transform in Q space was this triangular shaped function. Fourier transforms work both ways. Now, I've done this for just three special functions here, but in practice, the general ideas can apply to all sorts of different shapes. And we've given you a few more of them in the appendix at the end of Units 3 and 4. Right, so now we've cracked the problem of the single slit. And what's more, we've solved the problem for single slit with varying profiles. But how about the other problem that we posed right at the beginning of the program, that of the limited width diffraction grating? Well, perhaps the best way into this is to look at how we actually made the grating that Barry used in his laser setup earlier on. And I've got it here. All it was the diffraction grating in your home kit, and it's got a diameter which is much greater than the diameter of the laser beam, so to all intents and purposes this is an infinite grating, except what I've done is now stick black sticky tape down, leaving a very small gap, about 1/5 of a millimetre, between the two pieces. So now what I have is a slit which is narrower than the diameter of the laser beam. So this is now a restricted width grating. So how does this help the analysis? Well, what I'm saying is that a restricted grating with only a few pulses in it can be thought of as being made up of a single, fairly broad slit, but multiplied by an infinite grating. Now, is this a useful breakdown? Well, I think so, because we've broken the limited width grating down into two components that we already know the Fourier transforms of. The infinite grating Fourier transforms to this well-known series of harmonics, and the broad single slit transforms to a very narrow sinc function. Now, what we need is the Fourier transform of the limited width grating. But we know that the limited grating is equal to the infinite grating multiplied by the broad single slit. And we know the Fourier transforms of each of these components separately. So can we somehow combine these two component Fourier transforms to get the Fourier transform of the original limited width grating? Well, we might be in a better position to answer this question if we knew what that resultant Fourier transform looked like. Let's ask the computer. First, here's the infinite square wave grating with its frequency spectrum. Now, let me limit the width of this infinite grating. And the resulting frequency spectrum? Okay, what we've got here is a layout that follows the layout of the original harmonic spikes, but we don't have spikes anymore. What we've got is a series of wiggles. If you look carefully, I think you can see that they're actually narrow sinc functions turned upside down as appropriate where the original spikes were turned upside down. What we've done is not multiply the two component Fourier transforms, but rather we've done a sort of dealing act. We've dealt the narrow sinc function, which is the Fourier transform of the broad top hat, to all the positions indicated by the spikes in the Fourier transform of the infinite grating. We call this operation convolution. Perhaps what we ought to do now is have another look at the real diffraction pattern again.
Well, here it is. That's the diffraction pattern of our restricted grating. Does it bear any resemblance to what Keith has produced for us on the computer? Well, yes, indeed it does. You can see that around each of the main maxima there are subsidiary maxima. In fact, those arise from the sinc function, which is being dealt to each of the main maxima. Now, in fact, that was a relatively straightforward case. And it was straightforward because one of the functions that we were talking about, namely the infinite square wave grating, was in fact infinite. And that's relevant because it generated a Fourier spectrum which consisted of a series of well-separated spikes. And spikes, well-separated spikes, are easy to deal to. But what happens in a case when neither of the functions is infinite, that is, when neither of the Fourier spectra is spiky? Well, here is one such case. Let's store that. There are many ways of representing this as the product of two functions. One way is to start with a top hat and multiply it by a two-sided exponential. The top hat chops the wings off the two-sided exponential. To obtain the Fourier mate, we have to take the mate of the top hat and the mate of the two-sided exponential, which is a Lorentzian, and convolute them. But how? Well, one way is to take the Lorentzian and divide it up into strips. The sinc function is then dealt to each strip. All the sincs are then added together to give the resultant, which is the Fourier mate of our starting function. Well, we could in fact have got the same result by a rather different route. We could have split the sinc function up into strips and dealt the Lorentzian to each strip, and we would have come up with the same resultant. Well, what we've established is rather an important theorem. It's called the convolution theorem. What it says is that if we have a function a, which is equal to x times y, then the Fourier transform of a is equal to the Fourier transform of x convoluted with the Fourier transform of y. That funny symbol there, that cross with the circle around it, means convoluted with. And in fact, the convolution theorem works the other way around. If it's convenient to regard A as x convoluted with y, then the Fourier transform of A is equal to the Fourier transform of x times the Fourier transform of y. You see, all we have to do to get the inverse theorem is to exchange the multiply sign with the convoluted with sign. The importance of the convolution theorem is that it enables us to generate mates, Fourier mates, from mates that we already know.
Before we actually leave this topic of Fourier transforms, I want to show you what I think is really rather a nice demonstration. You see, all the way through this program, and in the main all the way through Units 3 and 4 as well, we've been talking primarily in terms of space profiles going to spatial frequencies. But historically, Fourier transforms were developed in terms of a profile in time going to a temporal set of frequencies. Now, what I want to do here is I want to show you the temporal equivalent of the limited width grating. And to do that, I'm going to use not a sinusoidal grating, but a sinusoidal oscillator. And I'm feeding the signal from this sinusoidal oscillator into a loudspeaker and into the oscilloscope so you can see what's happening. And I'll turn it on. You can hear that what we've got is a nice, clean, pure note, a pure tone. Mind you, I've not told you the whole story yet, because in fact what's happening is the signal from the oscillator is being routed through this box of homemade electronics. And what this box does is it turns the signal on, holds it on for a fixed length of time, and then turns it off again. And in fact, I can vary the length of time for which it's on. I can get it to be smaller and smaller. Now, that's equivalent to restricting the width of my diffraction grating. And if the theory is right, what should happen as I restrict the length of this pulse, then the spectrum should spread out. Now, I'm going to ask you to use your ears to tell what's happening to the spectrum. Let me go through the whole sequence. I've got to change the time base. Let me just have another go at that last one, but on an expanded time base. Now, I think you'll agree that what's happened with that last pulse is it's lost its pure tone. It's become a metallic click. Now, to an audio engineer, what that means is that there are lots of frequencies present, just what we predicted. So, yet another triumph for good old Fourier theory. In fact, I hope we've convinced you by now that this Fourier analysis is a really powerful technique. We'll be using it over and over again in this course, mainly in the spatial domain, but occasionally also in the temporal domain as well. And that should give you a very good motivation for getting to grips with these basic principles.